participate to this talk today, that I'm particularly happy to introduce you Professor Bruno Zatta. Bruno is professor at, I'm not sure about the pronunciation, Universidad Federal de Pelotas, okay, Brazil, and is a rather well-known researcher in the field of architectures for video coding. So this is one of the topics I worked during my research life, so it's one of my favorite topics, I would say, and that's why I'm particularly happy to have Bruno here today, so I don't want to steal you and Bruno time, and so I'm leaving him the floor for his talk. Thank you, and thank you, Bruno.
Thank you. Buongiorno, and that was all my Italian. No, I'm just kidding, but it's, although I can understand, I cannot really do a proper speech in Italian, so excuse me for that. I hope at least you can understand the main message from my English. In the back of the room, can you hear me? If it's not, I can try to speak louder or use the microphone. If you can hear, it's fine. So I'll try to move forward just with my voice. Let's see. So before starting, I suppose it's interesting to reinforce. I'm here to talk a little bit about my experience and actually my lab experience in video coding systems. Right? Call this title, right? It's energy efficient video systems design. So the idea, the main discussion here is how we can, and I'm not here to teach anyone, it's just to share some of our experiments and see, oh, this may be interesting, this may not be interesting when designing video system, particularly video coding systems, looking to an energy consumption perspective. That I would say would be the most important these days in many sort of devices, particularly mobile devices. I'll talk a little bit more, but I think there's no need to go stronger on that. My idea is to show a little bit about dedicated hardware design, but not much. I use a case study, and after that I want to discuss our later efforts in the direction of approximate memories or approximate storage, you may call as you prefer, and also near memory processing. These, I would say, they are younger efforts. So I'm not here also to present, oh, these are the latest and the best solutions, but some evaluations we have done and what we have learned from that I would like to share with you. I'm not doing this alone. I'll present later better the 5 names that are there. Of course, myself and 4 of my colleagues, but I'm return on that very briefly. So as I mentioned, I'm really far from home. So actually, I'm from the southmost state in Brazil. I was telling the guys here that this is the cold part of Brazil. Yeah, maybe interesting, but yeah, the coldest one we have at least. And it's really near to Uruguay and Argentina. And if we go, this is just Brazil, so we are down there at the Federal University of Pelotas. And yeah, Pelotas is like really bowl in Spanish. There's some history why this, the city is named after this boat, a sort of boat they used to carry meat around. I'm at the Center of Technology Development, the graduate program in computing, and also the group that we have built. Here just some picture from the university. Like, also I was mentioning, these are the old architecture that we have, probably like 250 years old. This is the oldest we can get in South Brazil. So that's why it's so interesting in terms of architecture here, staying here in Torino. And the research group that I mentioned, we call VTech, that's Video Technology Research Group, has been the name, we created the name in 2016, but of course we were doing our research way before that. But when 5 of us, we were joined, we are at the same university researching on the same topic, So we created this group. Myself, of course, in the first one because I'm speaking today, and Professor Daniel Palomino, Guilherme Correia, Luciano Agostini, and Marcelo Porto that are my partners in this. We have nearly, this number is always changing. Last week, one PhD student concluded, so probably this number is already outdated. 20-something, 20-ish PhD students, also 10 to 15 master students, and also in Brazil we try to bring undergrad students as I would call research assistants. So usually they help us in implementation, always working with one PhD and one master student. Also in Brazil we have this engineering takes 5 years. So usually those students, undergrad students that are working with us are usually in the last 2 years. So they can really handle very well many aspects of implementation. And we start training them in writing skills and also research skills that are really useful in the following steps. Just a picture. This is before COVID, so it's just to say, okay, there are people there. And after spending your time with this introduction, actually I should have, okay. I don't want to spend your time with basics. I don't know exactly how each one of you are familiar with video coding or video concepts in general. So my idea is really to go pretty quickly just to have a rough idea and some small points that are necessary to understand what we have been doing, right? So, of course, there are many challenges when we are talking about visual signal coding. It's video, but it's not just video, so that's why in this slide I'm calling visual signal coding. We may talk about video, but it goes further, right? Of course, there is image, but we have these days many immersive applications that require different sort of data. So I'll discuss a little bit more about that. But those new applications, here application would be virtual, mixed reality, and all those immersive devices, they may require more complex data representation. So there are a lot of challenge in working with those sort of varieties of data. There are new standards. Of course, as we evolve in the requirements, we need better tools. So we are always having new standards for coding, image not that much, video, light field, point clouds that are these new varieties of visual signals. And we want to do many multiple applications of such signals in, say, not powerful devices. Everything that you have on your pocket, like your smartphone or your tablet, you want to record maybe in 4K, 8K, or many cameras at the same time. So how can we do this in practice? The big thing here is that we are always fighting between two goals. We want to reduce the size of those files or that signal, and we want to do it in a way that the signal is good enough. And good enough depends on the application. I mean, usually when we are talking about, let's say, consumer electronics, we want to look at a video and say, oh, this is really sharp, this is looking nice. If we are talking about, let's say, object recognition, maybe the requirements are not that strong, depending on what sort of recognition you are doing. But you still need to do some sort of compression. So how you deal with the rate, the R, and the distortion, how you are destroying at some level your signal. This is what people that work on those standards, developing the standards, they are looking at R&D mostly. But there's another big thing to be considered, that is RDC, rate, distortion, and complexity. I like also to look at RDE, that's rate, distortion, and energy. So it means that, okay, you want to have good quality, you want to reduce the rate for representing any sort of signal, but you have limited like processing capabilities. So how can you deal with that? And as I mentioned, the sort of signal that we are dealing is always getting more and more complex, right? So this is, I just borrowed from Zhang, this nice plot. The data is getting more complex in the sense of, if we think about video, the resolutions are increasing, and also in terms of space, so you have larger pictures, and in terms of in the time domain. So we used to have like 30 FPS of 60, and people want 120, and you can even, depending on the application, have much more than that. So the data is getting more complex in this sense. It's also getting more complex in terms of the number of viewpoints that you may have. There is some, you can go to cinema and watch like 3D movies. It's not really a thing that people love. You have two views, one for right eye and another one for left eye. It's really limiting. I mean, you cannot like walk around and see different perspective of a scene. But there are, of course, other signals that are better in this sense, like not just stereo, but you may have multiple views. We are talking today about 3D also. You have views and you have depth. And you also may have different varieties of representation that I would say are more strong, like light fields. This is one example of a really small baseline, so dense light field that where, I mean, you have multiple views with different small displacement among them. So they are not really sparse, they are really dense, and they are really useful for some sort of application, especially to understand the scene. You may use that information. The depth is somehow hidden there already in the pixels content. So it's really interesting sort of data to be worked. But again, usually we work in a 16 by 16 array of images. So imagine an array of camera with 16 by 16 cameras. So we need to deal with that amount of data. Point clouds, I'm not going into this, but it's another representation that people are really evaluating these days, especially useful for mixed reality. These are static, like for a monument, for any historical object. You may have dynamic point clouds, like for self-driving cars, that it's really a hot topic in terms of application. Another dynamic point cloud, just to show you how this data has been changing and getting more complicated. Of course, you have quality, you need more bits, you want more bits to represent each color channel these days, HDR, HDR10, HDR, so keep increasing, right? Sometimes you don't have the devices to even differentiate anything, but yeah, you want the HDR, the best one possible. To deal with this increasing complexity, of course, this plot is just about video, right? But we can add other technologies related, let's say, to encode light field, for instance. But here we can have a rough idea in terms of history of the video codecs. H.261, no one cares about. MPEG-2, this was really a big deal in terms of industry. MPEG-4, H.264, another big hit. H.265 and VVC, that would be H.266 actually, if you want to give the numbering. I just pointed to some of those because those are, let's say, MPEG standards, right? This is not the correct naming, but everyone will understand, like, oh, these are MPEGs. There are other important ones. I will just point here AV1, that's state-of-the-art, royalty-free from Google and other huge companies. AV2 is coming probably really soon. And these, those small blocks, I would call generations. So after each generation, we can do better the job, so we can compress more, but we will see really soon how we need to pay in terms of that big arrow called complexity, right? All those standards, or almost all those standards, do basically the same thing. So this is a really simplified slide. So you can understand you have frames, images coming in. You may predict using intra and inter prediction, like in a way to guess, oh, that block should look like this or should look like that. Intra means that you are using space neighborhood to guess the content, and inter means that you are using temporal neighborhood. I mean, one frame is really looks like the other, like it's 30 FPS means 33 milliseconds, so it really doesn't change that much, so you can bring information from the previous frames. Once you make the prediction, you choose the best one, maybe intra, maybe inter. The error or the residue you can transform, quantize, and entropy encode. Entropy encode means like you just zip it all and send it to, or store or send it to whoever wants it. Of course, you need a closed loop, inverse quantization, inverse transform, so the predictors can use it as in a closed loop fashion. This is called hybrid video encoder. It's hybrid because there is prediction, there is transform base, and there is also, this will be enough to be hybrid, but there is also entropy encoding. So 3 styles, 3 ways to do the job, right? And we use all of them together to reach good numbers. And basically MPEG-2, H.264, HEVC, VVC, they all do the same. So what's new, right? We don't do for the entire frame at once. We partition, and those partitions can have different names like macro block, code inter units, so super blocks. And you start, for each one of those, you may partition it. Why would you partition it? You see this texture that you have here, it's really complicated here, not simple at all. So actually the example of partition is really bad in this case. Here it's flat, or flattish, right? So you may try to guess this part in a different way than you are guessing that one. So the way you partition is really to partition parts that look similar at some. This is really high level concept, right? It doesn't work like that all the time. But that's what you want to do. And you start partition. Let's pick one of those 64 by 664 blocks. So there are 4 blocks here. And we start partitioning. And you can evaluate, oh, let's try to do inter-prediction for that 64 by 64 block. Maybe a good guess. Let's try it. How do you predict? This is just an example for HEVC. You have 35 different forms, different ways to predict a given block. So take a 64 by 64 block and create different versions of prediction. Choose the best. Then you partition, as you can see in your left, partition in 32 by 32, 4 32 by 32 blocks. And then you try the 5 different modes of prediction. And you keep doing it. So you are reprocessing the same data multiple times. I'm not telling you that you must do all them, but this is the all effort, right? So this is the sort of problem. Oh, what's the best partitioning? And for each partition, what's the best prediction mode? Of course, I'm keeping it simple. Remember the transform? It used to be DCT. These days, there are a handful of different options that you can use. So 35 intermodes combined with like 5 different options of transforms. And inter is the easy part, right? If you go to interprediction, that's when you try to find good matchings in the previous frames. The way the tree grows is more complicated. You have more block sizes to evaluate. And evaluating each one of those blocks may require for each block to search in a previous frame in a given window. Usually we try to restrict that window so we don't search in the entire neighbor frame. And we don't search all positions. We use smarter algorithms to try to find a good guess. So usually you can, there's an object and you can find that object perfectly in the previous frame. Good for you. You are not sending any additional information probably, or just small few errors that you may want to send, right? It's usually not just for one frame that we are searching. You may search across many frames, combine them, and do crazy stuff, really. I mean, there are many options that you can use in current standards. That's why those combinations in terms of different prediction modes, I mentioned HEVC for interprediction, 35 modes. VVC has almost the double, different modes, different directions you can predict. When searching in the previous frame, this is the way we used to do until these days. Now you also have a fine motion estimation, means that you can, in addition to search in the reference frame, you can stretch it, use geometric transformation to find good matchings. So it's a complete new dimension of search. So you may search for each position and give a grade, and do this iteration in terms of that encoding loop many times. That's why if you are not familiar with the technology, this is just an HEVC or VVC encoder. It's the same as the other one. It's not, right? This is what the technology can be. This is probably what Netflix is doing when encoding like a huge processing farm. This is not what your cell phone is doing. It's not testing hundreds of combinations to find a good one. It's probably testing one or two. And of course, smartly, but it's not the same. I mean, you can use smart approaches. We are discussing that, but you cannot claim that you are really pushing the standard to its best, right? All those tools that have been increasing are roughly, we use this like a tongue rule. Every new generation we say, and you see, these are not the numbers that we are showing. We roughly say, the complexity of the encoding increasing 10x from one generation to another. This is roughly what we have seen. The first one is telling you, okay, it's 5 times, HEVC is 5 times more complex than H.264. Of course, it changes according to the experimental conditions. There's one important thing. This is about reference software. H.264, the reference software used to do all the combinations. HEVC does not do anymore. So it's not really fair to compare. So 5 times is really the all effort to the smarter approach. So we're not really comparing exactly the same thing. So that's why I think 10x, it's reasonable. And improving nearly 40% when compared to H.264. Next generation, VVC, 4 to 13 times. So again, depends on the configurations and so, when compared to HEVC, right? And the compression gains, I mean, crazy numbers. I don't think on average we can say that has achieved 50%, right? AV1, it's at the side, it's a different line of codecs. And also these experiments these days will change because the software that AV1, since there are those big companies working on it, in terms of computation effort has evolved a lot. So it is much more complex than HEVC. And no, it's not as efficient as VVC. That's what I can tell. Right? But when we want to make efficient systems, we need to understand how they behave, right? So this is just some scenarios about the VVC, and all those blocks that I showed you, VVC can go to blocks as large as 128 by 128. And here what we see is if you take one frame, or the average of all frames, this is how the area is covered by one given block size. Of course, 128 is huge when compared to 4 by 4 blocks, so you need to have many 4 by 4 to compensate one. This is the area. So yeah, we are using, this is probably 4K experiments. We are using a lot of this area is using 128 by 128. If you go to low resolution videos, of course, you are not using those huge blocks. You are probably using the other ones. So we can simply skip the smaller ones. Does it make sense? We don't need them. I mean, they are happening under 2%. Do you agree? Actually, this is not the case. When they happen, it's because they need to happen. We are talking about really detailed textures. We need that level of detail. Not always, but sometimes. And that's why we cannot simply say, oh, it's almost everything 128. You can try to do that, and you are just destroying the codec. But smaller block size is where the complexity or the encoding time, to be more fair, we are putting much more effort in those ones that are selected much less. So there's something that we can do. Maybe you can just go to those ones when they are really necessary. We can try to anticipate that. Just have a rough idea. I think the colors are not really good, but you don't see. I'll try to help in this one. You are going to see those blue boxes that are related to smaller ones near the object, and here are objects are people that are moving, right? In the background, you are probably seeing larger blocks. See, in this color, those colors represent larger blocks. I mean, maybe in this case, maybe it's not a really simple texture, but there's no motion, so probably it's just copying the block from the previous frame. So there is some information, the image, that we can use to anticipate some sort of decisions. Looking at the encoder itself, we know where the toughest problems are. So interprediction is usually responsible for something, it's those combining. We are talking about more than 50% of the computational effort or encoding time that we're spending there, right? So probably is one place where we want to try to build efficient systems. And that's it, basically. Really quickly, just a rough idea on what is the problem, right? Considering these sort of problems, myself and my colleagues, we try to make contributions in terms of, at one side, algorithms. So it's everything that's in your left side, and we are just not talking about this today. And at the right part, it's what here is called system level. But about system design, we are talking about different different parts that I want to discuss a little bit with you today. Hardware accelerators, I'll start from that. We have been doing this since ever, and have a lot of experience. Myself, I started working in a video decoder for H.264 when the Brazilian digital television system was about to be defined. So it was 2004. So we are developing a set-top box for real-time decoding of H.264. So we are doing this since a good time now. Architectural solutions. Here it's a little bit more to the higher level, and I want to show you one one work that we have done that we are trying really to bring some level of scalability using network on chips. I don't know if this is anyone is going to use, but it's something that we really want to evaluate. How we can use network on chips to provide approximation, variable approximation, and also scalability. And here, the memory part that I'm going to discuss with you about approximate memory and near memory processing. Right? Does it make sense? If you want, please interrupt me. I can stop and clarify an aspect at any point. Right? These just a list of contributions just to point it out, but as I mentioned, the most important certainly are those that we sent to Mauricio's book. Actually, he kindly invited us to submit chapters, and I contributed 2 of those, one related to 3D video coding, and the other one is a more general algorithm architecture design solution. So yeah, of course there are some journals, but the book is the most important right today. And pointing to that, because here I'm going to use as when I discuss hardware accelerators, I'm going to use one example that I really like. We have published it in TCSVT, that is Transaction on Circuit System for Video Technology. It's basically the same flavor as you have in interprediction. Right? But here I want to show you how we have done in terms of dedicated hardware and management of this hardware. Right? I remember the first conference I attended, people were bringing stuck hardware accelerators, just implementing the algorithm to any conference, and the rooms were like full. People were like closing the door because there was no room for anyone sitting or standing. That was about 2007, 2008. It was like this. Of course, we can keep developing hardware accelerators, but it's not like this anymore. We need to bring more, right? We need to bring smart management solutions. It's not just about this. This is the DCT. These are the inputs, outputs, and these are the numbers, right? Of course, we do this work. We need those accelerators, but when we are bringing like a transaction level work, people expect more, right? So in this case, we are talking about 3D video. So means that we have an array of cameras, and we are just sending information about a few of them as texture. That's image, basically, and some depth maps. So let's say you have 9 cameras. Just send the center one, the rightmost and the leftmost, and send depth maps. So you can use DIBR, depth image-based rendering, create any position in between, right? Here we have the same problem. For one frame, let's say in one camera, we need to find a good matching in the time before, time future. Let's say in the past frame. We can do that. It's interprediction, just like I explained you. But now you have neighboring cameras to your right and to your left. The information can be really useful. And we do just the same process. We just search for good matchings in the neighboring cameras in the same time instant. Make sense? We call this, just to have a different name, disparity estimation. Motion estimation along time, disparity along space, right? And that may be really useful. Usually, the number that comes to my mind, an MVC, that's previous generation, we could save nearly 20% of bit rate for roughly by adding that to. I'm not telling that's the same number, but just to have a rough idea, it pays off. And this big box is what we have done to solve the motion plus the disparity estimation for, in this case, for 3 views, but we can instantiate more. The first thing that you need to see For those that are far, I don't know how. This block here, it's called base view. The base view means usually the central one, right? If you have a non-3D display, you are just decoding the base view, right? And you are just decoding the texture. That means image. You are not decoding the depth maps. This is just useful if you want to generate another viewpoint, right? But we have, and in this case, also for the base view is not using the other ones. This is the first one to be encoded. So you are just saying motion estimation. Motion estimation, motion estimation, texture, depth. We have replicated that, or extended that to the other dependent views. In this case, our synthesis results are for 2 additional views. We can have more, where we have depth maps and texture. Inside of each one, you see motion estimation and disparity estimation. Same here, motion estimation, disparity estimation. So we are doing motion and disparity for all dependent views. And it means that we are processing a lot of data. And you see here, the orders are somehow changed. I tell you that this is going to be clear. Inside each one of those blocks, I don't want to go into details, just to show, okay, this is, for those that are familiar with hardware design, I mean, usual, we are using set trees, accumulators, sound comparators. This is the fractional motion estimation. So we can search in positions that are not like, we're not just moving one by one. You can move half pixel, quarter pixel, and this is the design inside. And this is just a sub tree. So it's adders and subtractors, and that's it, right? It's not here that's the contribution. This is just like others have done since a long time. I just didn't want you to keep open just big boxes is nothing. This is what is inside those big boxes. What we believe that is interesting is how we manage that. So there are a set of algorithms that we have developed for that. Fancy name, hardware-oriented TZS. TZS is the most widely searched algorithm these days, and but it's not really hardware-friendly. So he's really adaptive. He starts growing this shape here, and we don't know when exactly it stops. We decide, okay, let's put even more points, but let's make it predictable. So this is our hardware-friendly sort of solution. Not really a big contribution, but this is a way we use efficiently our processing cores. For everything that's in terms of dependent views, for the 3D HEVC, that's what's the case, we are always talking about horizontally displaced cameras. So we don't need to make vertical search. We just may have some sort of noise, but we do one-dimension search with refinement around. So let's use less data and do less processing. If we have a vertical alignment, we can change the parameters and do the same for the other direction. It's not a problem. We have strategies to bring the motion vectors from the texture to the depth map. Here we must do first texture, and after that we need to do the depth search. I mean, it's the same thing. If you have a good match in texture, it has usually or almost always is a good match also in terms of depth maps. So we don't need to do everything. So we are doing some sort of inheritance and using these to predict the search window. Remember, we are not searching in the previous frame, entire previous frame, but in part. We call this search window. The point is that if I know when object is far, think about perspective. If the object is far, when I'm searching for disparity, it has to be really near. If the object is closer, the displacement, imagine your left eye and right eye, the displacement is completely different, it's larger. So if the object is far and we have the depth maps, we can reduce the search range, we can reduce the search window. And we do this dynamically. So this is another strategy to make it better. So one of the hints that I want to bring is like jointly optimize algorithm and hardware. If possible, at the decoder can be a little bit less simple because the algorithms are more stuck, but there's still room for that. At the encoder, you can do really a lot of stuff. But there's the memory. That's usually the toughest part. Again, back in 2006, 2007, people were like producing thousands of hardware accelerators for video encoding. And if you were like about asking from how the data is arriving, many of them, boy, I did not consider that. People are doing like, I can process, let's say in 2007, I can process 4K. It was not the case, but people were not thinking about how the data is arriving, how they are spending. I'm reducing 5% in terms of processing energy, but what about memory? Memory usually is a huge footprint in those sort of systems. This is data-oriented, right? So we used all those sort of knowledge that we had, those algorithms like reducing search window to reduce the memory, or at least the active memory. We use that to dynamically turn off sectors of our on-chip memory. And here we have some savings. We also, it's basically simple to see that for depth maps, they are usually flat. We don't need to put much effort. We also have done some subsampling, and yeah, this is also working, reducing the memory footprint. And this is the second hint that I have, is that we need to optimize the memory. Actually, and along with the processing unit. Actually, these days I would say, no, we start from the memory, right? We have some works recently that we call memory center. If the memory is, by memory means the memory hierarchy, how the data is arriving when processing tends to be easier. Not always, but tends to be easier than that. And here I'm thinking really about those 4-dimension sort of data from light fields. If the data is arranged, it's easy to process. But if it's not, it's almost impossible. And these are just some results. In this case, we have really, this is just on-chip processing units and memory, S-run on-chip memory. External communication is not accounted here, right? So that is the baseline encoder for the motion disparate estimation. The second one is after reducing everything we could, like putting our algorithms there, but without runtime management. And the last one is with the runtime management, like turning off memory sectors, turning off processing units. And yeah, that's why I like those results. They are interesting. Any question? It's really not go to the details, just to have the rough idea, right? When we look to higher level solutions, I'd like to share with you this sort of approach we had. This was a partnership between us and Leandro from York University, and he's the NOC, Network on Chip expert. So how can we exploit the amazing features that a network on chip may provide us? And we are, by the time also, we need to do some sort of quality adaptive sort of solution. And we started with this one, right? Here, what we have is a 5x5 network on chip with 5x5 processing nodes. Some are for memory access, so the upper one, the GPP, it's not really processing, it's just bringing data and distributing. The other ones, it's solving our main algorithm problem, that's fractional motion estimation. It's fancy fear filter with another one, 2 dimensions. It's not complicated in its concept, but there's a lot of data to process. And we designed 4 levels of approximation. The 0 means precise, the other ones means worse, or more roughly approximated. And we want to use that to deliver scalability. So you see there are nested networks inside. If you are processing, I won't remember the names. Let's say if you are processing 1080p at 30 FPS, you are just using the 3x3 inside. If you need or demanding more, use the 4x4 and the 5x5. And you allocate the block that's being processed by different approximation levels according to characteristics of that block. If it's like a flat block, you can approximate like really strongly. If it's like more textured, you want to have precise or just slightly approximated. Of course, each one of those gives a different operation point in terms of energy consumption, right? And the tiles that I mentioned they were here. The numbers in terms comparing our maximum processing capability to the size of the network we need to use. And we have algorithms on top of that, like really to select which block is being processed where. I mean, we don't have all them available. This is fixed. We have a given number of FAP0, a given number of AP1, and so on. We need to find a good way to use that. For that, we use application knowledge. So this is the 2 steps and design time here, extraction and design time, we use to size and to select the number of each one of those processing units, average numbers. You can have some reasonable performance with that. But it's here, I think that's the most important contribution that's really doing at runtime. Oh, what is being processed where? This is not really simple to do. We have seen some interesting results. I'm going to direct to this one. And this is one magic number that tells you how good your encoder is. And large bars is bad. Okay? So FAP3 is the most roughly approximated one. So you expect large bars. So they're not good. If you use them all the time, you are saving energy, but you are destroying your coding efficiency. And at the other corner, you have, of course, FP0 is not here because there is no loss if the bar is at 0. What we want? We want to provide solutions that are energy efficient, so we can reduce energy, but we don't want to be here. We want to be somewhere closer to these bars. So that's what you see in this H, that's heuristic-based runtime manager, and the ML, that's machine learning-based management. It's not fancy. It's based on decision trees, right? And with those managers, we were able to reach 2.8 bit rate. So it means that we are increasing in 2.8% the size of the bit stream for the same quality, and reducing 48% of energy. I think it's good. And the other one, it's just a different operation point. It's not really better. I think it's slightly better, but we are losing 1% in terms of coding efficiency, but we're reducing less, 32%. We can, of course, design other managers that we can find apart. Actually, we have the Pareto curve and select where you want to operate at any given, when you're running out of battery. So you need to go to one corner or to other corner. 2 hints that I can extract from here. It's that adopting approximate computing can lead to good results, especially for video coding, for some of the blocks, right? And content-based management is something that it's necessary. If you want to be smart, you need to. It's about signal processing, right? It depends on the algorithms, but it strongly depends on the signal itself. So you need to anticipate the behavior at some point, at some extent. And finally, the last point that I want to discuss is about memories. These, as I mentioned, are younger efforts, but I really like them. I'm going to that one. And here, this is a partnership we have with UCI, University of California at Irvine, where I spent like 1 year. And those plots are just the motivation. These are, that one is SRAM, yeah, and these one are STT RAMs. Those plots are just showing that you can reduce, let's say, the voltage of your memories if you are willing to have some mistakes here and there. And again, reducing VDD is really powerful too. I mean, it's always squared, right? If you remember, you double VDD, you are increasing by 4 your consumption. So it's a powerful tool if you can use that. Of course, this is just one example. We can go further. Like if you are thinking about DRAM, we can play with the refresh ratio and so on. There are many knobs that we can play around. But here we're not really, this is just a motivation. We are not really on the technology side. It's just a tool that we have. We can change energy or performance for accuracy, right? Approximate memories or approximate storage. And we have done some works, and the final numbers are not here. They are not published, but at least I can give you one interesting idea. This is at the encoder side. We have done some fault injection, right, at the motion compensation. Again, the part that deals with the interframe prediction. To see the impact when we use approximate memory at the decoder. At the encoder, it's easier to mask that. If you are going strong in terms of approximation, the interprediction will look better. And it tends to compensate. So the experiments are much more complicated to be done. Here it's about the decoder. We have used this pin tool that's provided by Intel to insert faults. And we have run 100 times each experiment. This is a problem. Mauricio can correct me, but usually video-oriented experiments take a lot of time. And in this case, we're repeating it like 100 times because we are using a distribution in terms of, it's not like I don't know where the faults are happening. I know they are happening at once for every 1,000 or 10,000 bits, but I don't know when. So we need really to run it multiple times. We don't need to run it 100, but we have done this for understanding how it converts. And this is how it behaves. This is the quality. The higher you are bad in this case, because this is quality loss, it's PSNR loss. This is not the best metric, but it's the easiest one to understand for now. As you move right, you are having stronger error rates, 10 to -3. It's 1 bit flip for every 1,000 bits. This is not practical, but we wanted to evaluate. And here it's really low rate. This is somewhere it would make sense to be in current technologies. At least that's what we have seen. And this is one experiment. It means that this is already quite high loss. We are not willing to reach, let's say, 5 dB of quality loss, right? These are other experiments. Now, for different content, we have seen, 10 to the -6 can make sense. I mean, it's on average 0.2, 0.3, those bars here. This can be something that we can use. But I can tell you more. If you can dynamically adapt, we can go maybe to here and come back, depending on the content, right? It really changes with the content. If you can dynamically adapt, then we can make more benefit in this sense. We also have a behavior along the time. So this is time. We are, let's say, attacking, in this example, just intra blocks. And these are intra and intra frames. And all in between, we can see one given behavior. that's related to the number of intra-blocks that are there and the number, the distance between the specific frame and the intra-frame. It takes time to understand that, but it's just to show you that depending on the video content, depending on where you are in the encoding order, I just placed this structure here just to see, oh, there is one structure there. Depending on where you are in terms of coding structure, you can go further or you cannot, right? And we have already seen that it is possible to do a good, to reach good numbers, even at the decoder side. At the encoder side, we can go further, but we are still not published on that. The hint that we can extract here is, yeah, video coding is error tolerant, but it's not all tools. Right? There are some specific tools that make sense doing approximation. For instance, entropy coding, you cannot do that. If you miss one bit, everything is gone. But for interprediction, for intraprediction, for transform, for quantization, yeah, you can do. And how strongly can you push in each one of those specific memories? I'm considering private memories here. Depends, and you can really do a lot of job on tuning that and managing those approximation knobs. And yeah, approximate storage, I think it's really nice for this sort of application. Finally, just really, it took a little bit more time at the beginning. Even if you are using approximate memory, you need to bring that memory from external memory. It's a big part of the problem. So here, one idea, one discussion, this is another partnership. What can we do if we simply can avoid bringing the data? So this is the concept about near memory processing or in-memory processing. And the idea is really you have this memory stack and you process when you read it. And maybe you just send to your processing unit part of the information. You don't need to send everything. We use this architecture that's called VIMA, and that's vector in-memory architecture. We can process up to 2,000 parallel operations. And yeah, doing that works very well when in scenarios where the cache memory cannot handle. If your cache is working really nice for that application, don't even try this one, because you are bringing once and then it's doing its job. So that's why we use the decoder side, especially at the motion compensation, because usually you need to copy a part of a block from a previous frame and you are never copying it again. So your cache is not like working. You're just bringing data and you're using it once. It's worst case scenario for your cache memory. And the interprediction is, of course, the more complex one. And we have done some study. This blue part means we don't have to do nothing. So it's not useful to us. The other parts, the red parts, depends on the content, of course, is where we can do processing. So we designed this strategy. We have 2K operations in parallel, and we are processing always 2K by 128. That is the size 128 by 128 of this basic block of VVC. Every time that we consider, across these 2K parallel points, pixels, we are really using the result for, let's say, 70%, it pays off. If not, we don't do that. We just do the regular way. So it's basically what this algorithm selects. We call this coalescence. Otherwise, we are doing SIMD instructions that we have implemented in AVX 256. So we are doing using the CPU. And yeah, it was possible to reach speedups ranging from roughly 2 up to 22. And compared with the AVX solution, we were able to, this is in terms of, compared to the baseline, the performance improvement when compared to the AVX. So yeah, we can save memory readings and improve at this point, we were not able to give energy numbers. But of course, we are benefiting from that. Now we are just providing, at this point, performance results. So yeah, we are doing better in terms of performance. And of course, we are bringing less data. But we are not able at this point to quantify the energy savings, right? And yeah, the last one, I promise you. The last hint, that's avoid moving data. I mean, this is pretty basic, right? But especially on data-driven sort of application, this is really important, right? Let me conclude then. So yeah, visual signal processing, it's when we look at the coding, it's pretty mature, but there's a lot of things to be done when it comes both at system design and new data formats or new style algorithms. To name them, it's about all learning-based tools that people are working around, and yeah, I believe we are still seeing at least one generation of hybrid encoders, but after that we're moving directly to learning-based tools, or just maybe end-to-end learning-based encoders, and this is something that we need to keep track. New data formats, of course, and the system perspective. There are several challenges in terms of system perspective, and they grow as the data gets more complicated. So, yeah, algorithm level and also at system level. To finish, just, I mean, this is a group effort, so a part of our group effort, so thank, of course, all my colleagues, students, and partners across different universities. I'll be here in Torino until July, so this is my email. If you are interested in the topic, please reach me, or of course Mauricio will help by sharing emails of also if you, this is pretty complicated, right? Inf, doof, pel, do, br, so. And yeah, I'll be happy to handle questions if you have. Thank you.